Okay, so welcome back. And as I said earlier, I'll continue a little bit on the lecture before switching to the tutorial. Also, what I wanted to point is that now you have this tutorial book sheets with problem and solution problems and short questions, and now on the X side you also have the version available where the solutions are there. So we have covered many of them in the tutorial. Some of them are also still coming, but you can look at those also when you work through the tutorial problems, also in terms of your preparation for the exam. This is now available. And this, what we just discussed before the lecture ended, is actually also quite an important aspect. And there is a little bit of a flaw here in this, or it's not really a flaw, but I mean, how come that in this example, the law is not working anymore, the Ampere law, because actually we violated the regime where it is supposed to work. So we said the Ampere law is working whenever we deal with stationary currents. And this I also put in quotations here. During the charging process, if you just look at the wires, this seems to be like a stationary current. But as soon as you are moving here towards this capacitor element, there's a violation in the assumption that we are dealing with a stationary current problem here, because we had said earlier that stationary means that the charge is not accumulating in a volume. So the dq over dt should be zero. That was our assumption earlier when we said we are dealing with stationary currents. And in this example here, we have been deviating from this underlying assumption, and that's why we're also encountering some issue. So first, we were putting in here this control area, and it has some contour, some closed path along which we can evaluate our integral for Ampere's law. But then the second assumption is if we have a dome-shaped area that basically has its contour line at the same location as in this problem above, and so this dome is open at the bottom, so it's just this area here, then you can evaluate your integral over the current density over this area, and then you find that you get here the current that is flowing on top through through this dome to carry the charge from or to the electrode here. And you see, either assumption is valid. We have, either way, we have an area and we have the enclosing contour, the enclosing path that we integrate around. But depending on which area is basically part of this contour, we get different results, and this is a contradiction. And we have to adjust for that. And let's see how we adjust for that. But do you see how this comes about, this contradiction? Otherwise, please, this is also very important. Don't hesitate to ask. So you see, maybe I should mark that there's a bit of a violation to the concept of stationarity, because actually stationarity requires that there is no, this violates the assumption of stationarity, strictly speaking. But in this area where you have the wire, you could say, there I'm stationary. But here, at least when you reach this capacitor, there you have a changing Q over time, and that is our problem here. So we have a contradiction for time-varying processes. We have to extend Ampere's circuit law in order to be independent of the chosen area here. For time-varying processes, we have to extend Ampere's law, Ampere's circuit law, in order to be independent of the chosen area. So now let's look at the control volume here. And basically, the enclosing area of that volume now are the surfaces A1 and A2. Basically, we use this dome-like area and put as a lid the other area A1 there. So these two areas together, they actually form a volume. So we have here a volume V. And if you are, so you basically you have these two areas which are bounded, and you put A1 and A2 together, that gives you now a closed surface volume. And now we apply Gauss's law, and we use a control volume, V, and now we have an enclosing surface, an enclosing surface that is now this dV, and this is basically the surface A1 united with A2. So basically A1 plus A2. And there we can apply Gauss's law. We integrate over the enclosing area of the volume over the D field, and that means this enclosing surface is the combined surface of A and 2, sorry, the combined area of A and 2, and according to Gauss' law, that should be Q. So remind the vectorial surface element is given here in this form, where we have here is your surface element, and there's your normal vector. Your currents flow out here of that electrode and flow onto that electrode. So the field, the electric field that we have, that is actually only inside the capacitor. This is our dielectric displacement. And there's a flux only through surface A1. So we integrate over A1, 1, and 1. See, this is our normal vector here. And because that normal vector, as we have defined it here, is pointing inward, because this segment here of the surface originates from the area A1, and that's how we define the normal vector at that point. So in consequence, I put in here this minus, stems from the definition of normal vector. Now Q changes with time. Change of Q with time is our current through the surface 2. Now we use this one here. The change of time of the charge is an equal here to what we obtained from Gauss's law. That is equal to the temporal change of the flux. So you see the change of the charge with time, that is given on the electrode by the current, and the current that is assessed through whatever flows through the area 2. At the same time, we have from Gauss's law the correspondence that the integral over the area A1 over the electric flux density is equal to the charge. And so the change of charge then also conditions are change of the flux density here. And we see that when we insert here that upper relation. So now the current through the area A2 is, yeah, we actually have to include here a minus because the direction of current denotes the flow of the negative charges, right? So then we obtain here, and here the minus drops out then. Then we have here the area integral over the area 2 over the current density, and that yields, yeah, let's switch here the minus sign, we bring it on the other to the other side. The change of charge with time is minus the integral over the area A2 over the current density. So that refers to A2 here. On the other hand, if we look at the second contribution or the second way of expressing the temporal change of the charge via Gauss's law, then we have dq by dt is exactly this minus dt by respect to time. And we integrate here over the area 1. Now insert this here, or compare these two here. You see that your change of charge with time can be caused by a current, but it can be also caused by the temporal change of your electric flux density. So either of these quantities can cause here this dq to dt. And in that way, you can think of identifying this temporal change of the flux density as a current density. So you can identify the temporal change of flux density with a current density, and that is called the so-called electric displacement current. And if we go to Ampere's circuital law, we can make now a correction. The circuital law said that the integral over the closed contour of the closed path over the area is in the first case where we have the surface 1, A1, the area A1. We can give that here as the temporal derivative of the displacement field with respect to time, and we integrate that over the time. And for the second area, we would give the integral over the current density over the area. So that here would be for the case when the closed contour is actually for the area A1, and this here would be if it is actually for the area A2. So this change or this modification to Ampere's law, this is called the Maxwell's extension. So James Clerk Maxwell has recognized that there is something still missing, and we expand this law to the Maxwell's Ampere law. And that states that the contour integral over the closed contour of the enclosing the area over the magnetic field strengths here is equal to the integral over the area and integrating both the current density as well as the electric displacement current, which is penetrating this area. So this is our equation 3.31. And what it means, the 3.31 says that the magnetic fields are generated either by the electric currents or current densities or by the time varying electric displacement fields. So this is a very important, this is the essence of the extension here, that the magnetic field is generated either by electric currents or current densities, or by the time varying, by a time varying electric displacement. That would be basically by electric fields. Field D. So you have for the electric flux density now not just a spatial but also a temporal dependence. And then if you take the partial derivative here with respect to time, then this partial derivative only acts on the time component. That just a note on the side. So that's why you use here the partial derivative, because you have a function of multiple variables and you only take a derivative with respect to, in this case, the time. So this is now Ampere's Maxwell's circuitry law in integral form, and we can also bring that now into into differential form. And for that, well, I refer you here now to the mathematical handbook, but actually it wouldn't be also so hard to give a, well, it would, if you like, you can, the mathematical handbook, if you like, you can take a look at that at some time and prove it to yourself that this relation holds. Otherwise, yeah, if you take the area integral over a curl or the rotation of a vector quantity, then this is equivalent of taking the closed line integral over the enclosing line of this area over the vector quantity itself. And if you insert this relation here into our Ampere-Maxwell's law, then you will obtain the differential formulation. And this one here, this either in the integral or in differential form, but this Ampere-Maxwell circuitry law is actually the third of Maxwell's equations, or the third Maxwell equation, yeah. So the Maxwell equation composed out of a set of 4 equations plus 2 constitutive relations, and they describe the electromagnetic wave phenomenon. So the curl of the H field is equal to the current density and the temporal change of the electric flux density. This is equation 3.32. And this one here describes here, if you look now at the D and the H that you here have here, you obtain here a coupling between, well, actually between E and D, that is by the constitutive relations, but you have here, you know that relation already. So you have a coupling between E and D on the one side and the B and H field on the other side. This is given to you by Ampere-Maxwell's law. Now, to get a little bit back without too much detail, what we had discussed about the electrostatic field, we said the E field is a conservative field. How does it look for the magnetic field? Are magnetic fields? Well, if you look at the curl of the magnetic field, then this is not always, but in general, it can be different from 0. And that means also that the closed contour closed path integral over the H field, that is different from 0, possibly. And this is very different. You know, remember the electrostatic field. If we integrated the electric field on a path, the electrostatic field on a path that is closed, it will always, the result would always be zero. So that is not the case for the magnetic field. So when is this zero? We can, of course, also have the situation that a closed line integral over the magnetic field becomes zero. That is possible, but that also means that there is actually no magnetic field. The magnetic field is vanishing there. Then this solution can be obtained. So 3.32 and 3.31. That 3.31 is the integral form, and 3.32 or 332, that is the same thing in differential form. And they tell you both how the magnetic field is generated. And these are the third Maxwell equation, the one missing only. So important to take along from the 3.7, we have earlier introduced the Ampere's circuit law, and we have seen now that there is a contradiction, but basically only when we are not dealing with stationary currents here anymore. And this charging of the capacitor is not a stationary current phenomenon anymore, because we have accumulation of charge in this volume. But we see, if we then take into consideration also the Gauss's law, then we see that the change of the dielectric flux with time, that depends also on the temporal change of the charge. And if we include that for the Ampere law, then we get a proper formulation that holds true also in the non-stationary case. And that means we have expanded the law here by integrating not only over the current through this control area, but also taking into account, as here, I mean, not only the current density, but also taking into account the temporal change of the flux density. So the temporal change of the flux density is an electric displacement current. And you have to take both of these components into account. Then your law is so much complete that it is also applicable to the non-stationary case. Quick comparison: if you look at electricity and magnetism, the electrostatic field versus the magnetostatic field. So you have forces here on the E field, no, forces due to the E field. If you are looking in the electrostatic case, you have the Coulomb force that is acting both on resting and also on moving charges, and the field is generated by electric charges. On the other hand, if you look at the magnetic field, then you have here a force which is acting on moving charges which are moving through a magnetic field experience a force that is a so-called Lorentz force. And moving charges also are constituting the electric current. So there's no such thing as magnetic charges. For the electric field, you know that Gauss' law is very essential because it relates the electric flux density to the charges, to the sources. But the magnetic field does not have sources in a mathematical sense. It has quantities which are generating the field, but it only has field lines which are closed, and there is no place, no point that they originate out of or ending. So that is therefore a solenoidal field, the magnetic field, And that means if you are doing the equivalent of Gauss's law, that means if you're taking the closed surface integration over the magnetic induction, it will be always zero. So the sources of the electrostatic field, those are the charges, and there are, however, no magnetic charges and no magnetic monopoles. The B field is solenoidal. You see here comparison of the field lines. So field lines start and end at electric charges for the electrostatic field. And also you have a conservative field. That means if you are integrating the field along some closed loop path, then it is always vanishing. That implies also that the rotation or the curl of your electric field is vanishing. This is different from the magnetic field. This is not a conservative field. So it is no potential field and not a gradient field. So your curl of B is not vanishing. In terms of the generating quantities, you have here, when you take the mathematical description, in the electrostatic case, you have that by Gauss's law, and you have the Poisson equation. So the charges or the spatial charge density is giving rise to your electric displacement field. And when you look at the generating quantities, then you have to use in the magnetostatic case the Ampere circuital law. So a flowing current gives rise to your magnetic field strengths. If you look at the comparison of the E and B field, how do they correspond to each other? The E field, it takes the material properties into account. The E field is, so to say, you're directly related to your force field, and it is a measurable field. In that sense, it relates to the magnetic induction or the magnetic flux density, the B field, which also takes into account the material properties. And it is also the field that is responsible for the force, and that is, so to say, the measurable field. If you measure something, you will measure the B field. If you compare then the D and H field, then the D field, it takes only into account the field generating quantities. That means this charges, and has gotten rid of the material properties. You see the D field is times a permittivity times the electric field, but remember that when you were looking at the origin of the electrostatic field, that originates from the Coulomb force, and you had the Coulomb force, which was 1 over 4 pi epsilon naught. So you had brought in the material properties there in the denominator, and from that force field you have obtained the electric field by taking F over Q, right? So the D field is basically without your material parameters. And so is it for the magnetostatic case. The magnetic field strength, it takes into account only the field generating quantities. So those are the electric currents, and it does away with the material properties. And then we have seen that in the case where our stationarity assumptions are not strictly adhered to anymore, we have to make an expansion of the Ampere law, and we have then Ampere-Maxwell's circuital law. And there you see that now you have a coupling between the electric field and the magnetic field. And this you see here in the bottom slide. Now, there's one part missing, and that is the inductions. And that means that electric fields can also be generated by a time-varying magnetic field. that we will take care of in the next chapter. And then we have everything to put together our Maxwell's equation. And now let's switch over to the tutorial. So last time we were looking at some capacitor problems, and then actually we switched to look at some problems where we had to take the conductivity of wires into account. And there we looked at possible uh, distributions along the x direction for the conductivity and what densities of carriers can go along with it. And then let's look at, this is a very quick and short problem. This is a resistance of a circuit which is applied where you apply a voltage. And this circuit is stepwise extended as shown in the figure below. So you see first you have a single resistance, then you have two of them in series and two of them in parallel. So they all have the same properties, these resistors here, these individual ones. And now you connect three in series, but you put three in parallel of these three series each. And now the quick question is, what statement is true? The power consumption of the circuit is stepwise, half, doubled, increased by a factor square root over 2, or unchanged. And we can quickly take a look at that by denoting this here as our first, second, and third step. So in the first step, we have our total resistance equal to R. That's where we start out. In the second step, our total resistance becomes. So you have first, so you have on the one hand a series connection, and you on the other hand also put them in parallel. So if you put two resistors in series, you double the resistance. So this here becomes 2R. But now you put them also in parallel. So you have to add up the total one over the total resistance is 1 over the individual ones. So you see that this gives you 2 over 2R, and taking the inverse here, that is just again the same resistance value. And in the third problem, you have the total by taking three resistors in series and then switching three of these series connections in parallel. So then you have 1 over 3R plus 1 over 3R plus 1 over 3R. And you take the inverse here. So it gives you 3 over 3R to the minus 1 is R. And you see the asked is the power consumption. The power consumption is current times voltage, or you can also give it as voltage squared over R. And then you see the correct answer is D. D is the correct answer. The power remains unchanged. Let's go to the problem number 20 from our tutorial problems, and that is a gas charge tube, gas discharge tube. So you see that graphed here. You have a little tube in cylindrical shape. This is your coordinate system. This is radial direction. It is aligned in Z direction. You have an angle phi here. And you have here a current density that has a radial dependence. So what is the question problem sound like. So that is the interior of a cylindrical symmetric gas discharge tube with a radius A, it's equal to 1 centimeter, is filled with a conductive plasma of charge carriers, which flow parallel to the cylindrical axis, which is the z-axis. And the electric current density has only a z component, which depends on the radial coordinate r as follows. So for r smaller or equal to a, it is this current density is a constant J0 times 1 minus r square over a square. And that constant J0 is given with 20 ampere per square centimeters. And for the radius larger than a, your current density is vanishing. So question, what is the total current flowing through the discharge tube? Well, we obtain that by integrating over a surface A. Let's depict that here. R. This is our Z orientation. You have here A, where the discharge tube extends to. It should be, of course, it is symmetric here. Then this here is basically your Z component. You have here your radial component and here your phi component. And up there we describe the area with a normal vector here. And if you look at the current distribution, that is a constant value times 1 minus r square over a square. That means we have something that looks like this. This is our absolute value. So it is maximum at r equal to 0, and then it has this decay 1 minus r square a square and 0 everywhere else. So this is for r smaller equal to a, and this is for r larger than a. So let's integrate over the current density that goes through this area element that I have graphed in there. And now, because we are working with cylindrical coordinates, you have to remember that you have the top surface of a cylinder. The differential surface element is given then this normal vector oriented in z direction, and it is r times d phi dr. So let's use that. Then we obtain here from 0 to a and from 0 to 2 pi. And we put in here the value of the current density, 1 minus r squared over a squared. And we integrate over the surface element dA, that is Ez. Wait a moment, the first Ez is actually still from our current density. This is from our vectorial surface element d phi dr. And that gives us, because there's no phi dependence on the current density, the integration from 0 to 2 pi just yields 2 pi j naught. And we integrate from 0 to a. And we have this r here that comes from that surface element that we have to consider. So then we obtain here r minus r to the power of 3 over a. And we integrate over dr. And that gives us 2 pi j naught. R integrated is r squared half. And the r to the power of 3 integrated is r to the power of 4 over 4a squared here. Boundaries are 0 to a, and that is then 2 pi j0 we insert that for r is a squared half minus a to the power of 4 divided through 4a squared. And if you look at that, you can take out here a squared and make this an a squared up there. You just cancel the a squared, and then you get a squared half minus a squared fourth. That gives you 1/4 a squared. And this is pi half j naught a squared. Now insert the values given. You have given here the j naught as this. You have given the a as 1 centimeter. And so you obtain pi over 2 times 20 a over ampere per square centimeter times 1 squared centimeter squared. And then you obtain 31.4 ampere. The next question was B, calculate the magnetic field strength inside the discharge tube. That is for R larger than 0 but smaller than A, and also for outside where R is larger than A. So B, we have to take the enclosing line of the area and integrate over the H field. And if you have a top view now, see, this was our side view. Our top view is basically, you have here your A again, and you have here your dr element here, and this is z direction here, and this is your phi. And now you want to integrate along a circular path that can vary in radius with r, and that radius can be such that the circular path is within that range where there is still the inside the discharge tube, or it can be also outside of it. So integrate over the density, then you get a current dependent on the area. And this integral on the left-hand side, because we are looking at a circular line then, and because of the symmetry, you see that the current density has only a radial dependence. And due to this symmetry, we know that our H field component, or H field, has only a phi component. And the line element for the circular integration from the vectorial dr, that is also oriented in phi direction, times r d phi. So this is what we have to evaluate on the left-hand side. And that gives us, because we have no variation with phi, that gives us just 2 pi r times h phi of r. And that means the h phi of r is always here in this problem the current enclosed or flowing through that control area divided by 2 pi r. So we have our region 1, which runs from 0 to A, and there our current, also a function of the area, which is a function of the radius, is 2 pi j naught. How do we know this? Because we basically have here already done that, where we, however, have chosen integration boundaries from 0 to A. Now we use the same here, but we have our integration boundary from not from 0 to A, but from 0 to R. So you can insert that here right away. So you get the R prime, which I denote to avoid confusion with the boundary of the integral, minus r prime to the power of 4 divided by 4a squared, and our boundaries are 0 to r. You compare that, you see this is just what we had here. So let's just insert that. 2 pi j 0 r squared half minus r to the power 4 divided by 4a squared. And then take this part here, just divide the current by 2 pi r, and then we have our h phi is 2 pi j 0 r squared half minus r4 divided by 4a squared, everything divided by 2 pi r. And that would be j naught r over 2 minus r to the power of 3 over 4a squared. And that is our field for r larger than 0 but equal or smaller than a. And in region 2, this is where our r is larger than a. So basically, you remember this scenario where this is our a, and we evaluate it on a circular line inside. A as in this is our tube, basically this is our complete tube. This is, and so we always evaluate the circle integral along the control area, but this shall here indicate that this whole thing is our discharge tube, and we are here on a circle and have a control area that is smaller than the discharge tube. So this is our A here. But now in the second case, we have again our discharge tube. So here, this would be our control area A. And now we have a control area A here. And we assess the E field, the magnetic field here. So then we have the phi component or the H field again. A is the current as a function of the area, 2 pi over r. But now we see that we are outside of this discharge tube. So only within the discharge tube we get a contribution to the current through that area. So we can use the total current that we have already computed in A, and that's just this phi over 2 times j naught times a squared and divided by 2 pi over r. And that is again then j naught times a squared over 4 times 1 over r for r larger than a. So you see now the current is fixed because no matter how much larger we make our r, we don't obtain more current flowing through that area. So that remains then in this region a constant. But of course, this r is varying, so you have a 1 over r decay on the E field. And so now the question is, we have completed B. Now C is at which distance r sub m from the cylindrical axis does the h phi retain its maximum value? What is the maximum value? Well, we have to take the derivative of the h field with respect to r, because you want to get the max value of a function. Let's say you have here some arbitrary function. This is some function x, and you want to see where are the maximums. So you take the first derivative, and that would be something like that. It has a, how that matches it roughly, but here you basically get the slope of the function, And where it has a maximum, the slope of the function will be exactly 0. So here it has maximum and minimum values. And if you want to determine if you have a max or minimum value, first thing is you take the first derivative. That tells you that you have an extremal value, maximum or minimal value. And then you take the second derivative, and that will tell you whether um, whether this is actually a maximum or a minimum, depending on whether it is positive, in which case it will be a minimum, and if it's a maximum, then it will be negative. So this is a way we can evaluate that. We basically have here the function of h of the magnetic field as a function of r, and let's just take the derivative with respect to r, that is d. So let's take the derivative. The r half will be 1/2, and the r to the power of 3 divided by 4 over a squared, that will give us 3/4 r squared over a squared. And now that should be 0. That means 1/2 minus 3/4 r squared over a squared times j naught is 0. And that is, of course, the case when the j naught does not matter here. But if r squared is 2, we just resolve for what is in the first bracket here. The first whatever is here, we set that to 0, and that means r squared is 2/3 over a squared, 2/3 times a squared, and that is basically our value Rm that we have thought for. So we just take the square root of that previous line here. This gives us square root of 2 over 3 times a. And check, is this really a maximum? Because for the maximum, the second derivative has to be smaller than 0. And that would be, just take another derivative. Just take here the derivative. 1/2 has no r dependence, it's vanishing. Here you take r squared derivative is 2 times r. So 2 times 3/4 is 6/4 r over a squared. Well, and that, you see, will be always 0. That's fine, because r will be also some value which is larger than 0. Okay, so we have found the distance from the cylindrical axis where we obtain the maximum value. And now we want to find what is this value of the field once at the radius r equal to a, where the discharge tube ends, and one where we expect the maximum, where we not expect, we have determined that there's a maximum value. This is our problem D. That tells us now we should obtain h phi for r equal to a. That means we take a of, which is a function of the control area, and that again of the radius, and we divide it by 2 pi over a. The r is equal to a. And then you insert again these values that we have obtained for the total current, and you obtain here 5 ampere per centimeter. That's our H field at position A. And if you look at the radius r is equal to Rm, that means H phi, where r is equal to 2/3 of A, then you obtain by inserting the values 5.44 ampere per centimeter. That is our Hm. And the last question is now, plot the hv as a function of r. H is a function of r. It only has a phi component, and that is dependent on which region you're in, either the j0 times r over 1/2, r over 2, r to the power of 3, or a square, that what we computed before. And the other one would be j naught a square over, we have there, this is, okay, so you have h of phi versus r, you have here rm and a, you have there the maximum value, hm, and at hr, you have the value ha. Here, you're inside the discharge tube, and here you're outside. So you have here